The energy that drives the climate system comes from the sun. When the sun's energy reaches the Earth, it is partially absorbed in different parts of the climate system. The absorbed energy is converted back into heat, which causes the Earth to warm up and makes it habitable. The sun and its energy. The sun is the star located at the center of our planetary system. It is composed mainly of hydrogen and helium. In the sun's interior, a thermonuclear fusion reaction converts the hydrogen into helium, releasing huge amounts of energy. The energy created by the fusion reaction is converted into thermal energy, heat, and raises the temperature of the sun to levels that are about 20 times larger than that of Earth's surface. The solar heat energy travels through space in form of electromagnetic waves, enabling the transfer of heat through a process known as radiation. Solar radiation occurs over a wide range of wavelengths. However, the energy of solar radiation is not divided evenly over all wavelengths, but is rather sharply centered on the wavelength band of 0.2 to 2 micrometers. The main range of solar radiation includes ultraviolet radiation, visible radiation, and infrared radiation. The Sun is located at the center of our solar system, at a distance of 150 times 10 to the 6th kilometers from Earth. With a surface temperature of 5,780 Kelvin, the energy flux at the surface of the Sun is approximately 63 times 10 to the 6 watts per meter squared. Properties of solar radiation. To find the energy flux, we must use the Stefan-Boltzmann law, which states that I equals sigma T to the fourth. I is expressed in units of watts per meter squared, T is in units of Kelvin, and sigma is a constant equal to 5.67 times 10 to the negative 8 watts. To do this, we must put I equal to 5.67 times 10 to the negative 8 times the sun's surface temperature, which is 5,780 to the fourth power. This yields 63,284,071.5 watts per meter squared. The average annual radiative solar flux at the top of the Earth's atmosphere is 1,360 watts per meter squared. It is sometimes referred to as the solar constant because it has changed by no more than a few percent over the recent history of the Earth, the last few hundred years. The Earth's albedo. The Earth's surface reflects, that is, returns the radiation back to space in more or less the same spectrum, part of the solar energy. This is what makes the part of the Earth lit by the sun visible from space, in the same way that the moon and other members of the solar system are visible to us, despite their lack of an inner source of visible radiation. The most obvious aspect is the brightness of Earth's cloud cover. A significant part of Earth's reflectivity can be attributed to clouds. In climate texts, the reflectivity of a planet is referred to as the albedo. That is, albedo equals reflectivity, and is expressed as a fraction. The albedo of Earth depends on the geographical location, surface properties, and the weather. On average, however, the Earth's albedo is about 0.3. This fraction of incoming radiation is reflected back into space. The other, 0.7 part of the incoming solar radiation is absorbed by our planet. To find how much energy is received by the Earth, we need to find the solar radiation incident in Earth's disk. This is 1,360 watts per square meter, comparable to energy incident on a flat horizontal surface when the sun is directly overhead on a clear day. We need to multiply the incoming solar energy by a factor of 1/4, the ratio of area of the Earth's disk, pi r squared, to the Earth's surface area, 4 pi r squared. You can think of this as spreading out the incident solar radiation uniformly over the Earth's surface, the night side of the Earth as well as the day side. This is 1,360 divided by 4, yielding 340 watts per square meter. Then we need to multiply by the factor of 0.64, which takes into account the fact that 36% of the incident solar radiation is reflected back into space by clouds, snow, and ice, and the light-colored sands of the deserts. The 0.64 is equivalent to the factor 1 minus A in the formula of the text, where A is the Earth's albedo. To calculate the effective temperature, we need to use the Stefan-Boltzmann law, which says that the emitted radiation is equal to a constant times the effective radiating temperature raised to the fourth power. To solve this equation, all we need to do is divide the emitted radiation, 217.6 watts per square meter, by the constant 5.67 times 10 to the negative 8th power, and take a fourth root of the result. Dividing, we obtain 3.83 times 10 to the 9th power. Now we have to take a fourth root of this. The calculated result is 248.89 Kelvin. The effective temperature of Earth is much lower than what we experience. The surface temperature of our planet is about 288 Kelvin. This difference is in the effect of the heat-absorbing components of our atmosphere. This effect is known as the greenhouse effect, referring to the farming practices of warming garden plots by covering them with glass or plastic enclosure. The Earth's atmosphere contains many trace, or minor, components. While the major atmospheric components, nitrogen and oxygen, absorb little or no radiation, some of the minor components are effective absorbers. Particularly effective is water vapor, which absorbs effectively in the infrared wavelength range. Because the atmosphere is almost transparent to sunlight, all that is absorbed in the surface results in warming and the emission of infrared radiation. This radiation cannot freely escape into space because of absorption in the atmosphere by trace gases, such as water vapor and carbon dioxide. These absorbing gases and their surrounding air warm up, emitting radiation downwards, towards the Earth's surface, as well as upwards towards space. This effectively traps part of the infrared radiation between the ground and the lower 10 kilometers of the atmosphere. This reduction in the efficiency of Earth to lose heat causes the surface temperature to rise above the effective temperature calculated above, until finally enough heat is able to escape to space to balance the incoming solar radiation.